The subject we're going to talk about today is something I call Java at speed. There'll be self-evidence why Java and speed are in there in a little while. I like to have this slide up in a lot of talks that I give, just as background to start with. Anybody here recognize what that thing is? I know you know. So that is the Apollo 13 CO2 scrubber. This is the ultimate example of heroic duct tape engineering. Like literally taking a square peg, getting it to fit in the round hole, saving people's lives from hundreds of thousands of miles away. This really happened. This is not the actual one because the actual one burnt in reentry. This is the one they had on the ground for the practice thing for the engineers to work on. And you know, every once in a while in a career you might get to do something that feels so amazing. Like you save the day, you hopefully not with people's lives on the line. And you get something heroic done, something impossible on a deadline, it's got to get done, and you did it, and you did it in some really ingenious way. And there's this amazing feeling that comes with doing that. I mean, if you're lucky, you get to do that a few times in your career. But right along with doing that comes the realization that most of your job is to make sure that never needs to get done again. That the next time people won't have to duct tape a CO2 scrubber in to make it work. You should study these things. You should learn from them. You should learn hard. Like, I'm assuming they realize that next time all the CO2 scrubbers in the spaceship need to be the same and use the same filters, right? And that part of, you know, duct tape engineering is an amazing, exhilarating thing to do. Having the skills to do it is probably important, good practice. But at the same time, every time you see a lot of duct tape on your code, on your systems, there's something wrong with them. There's something you're putting duct tape over. There's something that you're going through heroics for. So keep that in mind. We might touch on it later in the talk. So today we're going to talk about Java at speed, kind of getting the most out of the systems you're running on. And at a high level, we're going to kind of cover some introduction and motivation, talk about some of the hardware trends and the features that we have now, look at some compiler stuff, simple compiler things, what compilers could do to code, take a detour into some micro-benchmarking, not a lot, but enough to scare people, and then go back into compiler stuff and talk about some cooler, speculative, interesting compiler things. Then talk about how warmup works and how this sort of comes together in a running system and a little bit of what you can do about this if you put it all together. Sort of the rough agenda we're going to go through. A little about me. I'm the co-founder of Azul Systems, the CTO there. At Azul, we make Java virtual machines. That's all that we do. And one of the things I've worked on a lot that people know me for probably is garbage collection. Here's some evidence of me working on garbage collection in my kitchen. This machine is a trash compactor. In California, we actually have those. We're really lazy. And what a trash compactor does is it performs minor GC compactions during the week, so you only have to do the full GC on the garbage bag once a week on the weekend, hopefully, right? And that's maybe why we have generational GC in software, because we learned from that. In this case, the compactor wasn't working right. I had a fragmentation problem. And you can see I had to go fix it and manually defragment the heap of garbage in there. And then, you know, I thought it would be really funny to take a picture with the book. And that was 14 years ago. So it's been a while. I've built a lot of things and made a lot of mistakes. We don't need to get into all of them. I learned only from a few of them. And then at Azul, we make Java virtual machines. Java speed and latency and responsiveness is sort of what we focus on. So we tend to know a little about the field, and we're proud about what we do, but we also kind of see what everybody else is doing in Java and can talk about it generically. Another subject I like to talk about, which I won't cover here, is how badly we all measure things. and how many mistakes we do when we make those. You can find talks of mine called things like how not to measure latency, and you could enjoy those if you want. So the subject is speed. What is it good for? Absolutely nothing. Say it again. No, but what is it good for? Speed needs context. There's a purpose when we talk about it. For example, are we fast when it matters? Are we fast all the time, or only between the times where we release code? What if we release code 27 times a day, and every time we release code, 10,000 slow transactions happen? That's 270,000 slow transactions on every server every day. That's a lot of slow, right? Fast in between them is interesting. Are we fast at high loads, at peak times, when it matters for whatever the system is doing, or just in between? Are we fast when the market opens, if we're trading? Are we fast when we actually do a trade? For example, maybe I have an algo system and it listens to the market really, really fast, but it only trades 100 times a day, and it's running interpreted code when it does that. That's not a maybe, right? By the way, if you're only trading 100 times a day, that's probably what's happening to you in Java. And are you reliably fast? So are you fast when you measure it? Is it really that fast? Or if you run too long, it's not going to be that fast. Something bad will happen, right? So these are all kinds of questions about, qualities of speed, or when it matters, or what you can use it for. Now, we'd like speed to look like this. It's just a number. It's always the same. It's just fast. How fast? Fast, But the reality, especially for Java, looks more like this. That's the actual behavior of speed over time in the JVM. So what is that about? Why? What's going into this picture? And I'll break it down into pieces. Now, the beginning part is that in the Java world, we generally start with code that we haven't yet run and is not warm and is just loaded and is running interpreted. That's this yellow stuff on the left. Most of our code, at the very beginning, all of our code is interpreted. Now, as the JVMs see that interpreted code running, they pay attention to it. They say, oh, I'm running this a lot, let's make it faster. And they spend energy on doing that. The first step is they'll compile it to something better than interpreted. It's not really fast, it's faster. Its main purpose of this step of compilation is to gather information. So it's going to run faster, and it's also going to collect a lot of useful information so that we can figure out how to make it fast. And then with that information, the profiling information, we then truly optimize the code, which is what this blue stuff is, to make it go fast for the situation we're seeing, for this profile, for this behavior. And JIT compilers and JVMs are good at doing these transitions. We've been doing this for 20 years now. But this is a learning process that starts every time you start running code. And it's an evolving process. It's done on a per method basis. Every method that you run goes through this. It only goes through this if it has been run and run enough times, or long enough. Okay? So what does this translate to in speed? Well, let's start with response time. If we look at response time over time, this is what it'll look like. You start with the slow code, so it takes a long time to respond. And then as that mix of code starts getting more and more of the green compiled, not quite fast, but faster stuff, it gets better. And over time, it gets eventually replaced with all blue stuff. Good, fast code. Now, in addition to that transition, you have all these spikes in the middle. Those red spikes are, call them what you want, stalls, hiccups, pauses. Garbage collection pauses are one key example of what causes this, but there are other pauses that make things happen like this, whatever your system happens to be doing. So the disruptions in there are much higher. If we take this response time plot and invert it, this is what speed looks like over time. We start slow, we get faster and faster and faster and faster because the code gets replaced with faster and faster code. Eventually, all we're running is optimized code, and we're at this sort of a plateau of speed in a common case, but we still have these dips to an absolute zero speed for a little while, and then back to really fast all over the time. like they say, the Java is really, really fast eventually between terrible, terrible stalls. That's where we are in most environments today. So that's what this picture is about. An evolving thing going through. Now this evolving thing is not just a direct transition. You can see that there's back and forth in spikes, and we'll talk about why those happen as well. But that's context for the shape of speed. Let's talk about the environments we're running on today. So a modern server, and I'm mostly looking at servers, it's probably applicable to other systems too. Looking at the Intel universe at least, which is what we most run on, looks like this. You can see the evolution of chips, you can see the evolution of chips over time, the number of cores we get, the cool names we give them. This second from the right column is features, and features are important. In addition to just having more silicon and more speed and more room, we also get features that let us do richer things or more things with the same instruction set or with new instructions. Right now, we're right around here. If you're running on a cloud environment, you're probably running one of these two architectures. If you're buying a new server today, it's the last one on the list. And if you have old servers, you're probably a couple generations back. So these features, these AVX and BMI and TSX and AVX512s are important because they let our servers do new things if we know they can do them and if we actually make the code use them. Now those individual cores also get better at other things implicitly. For example, the amount of stuff they could do at the same time keeps getting better. This shows you the number of out-of-order execution things that could be done. Think of it as a juggling act with 224 balls up in the air. When one comes back, you send another one up. That's what CPUs do today. And in those, there could be 72 loads and 56 stores all at the same time. We're just waiting for them to complete. And the CPUs are really good at figuring out how to move this forward, so good that it's very hard for a human to model that well. Like, we can't just look at a piece of code and say, that's what the CPU is going to do with it exactly. This is a nice complex picture we're not going to get into of how things flow through a CPU, through fetching things at the top and decoding them and then executing them and eventually dealing with memory at the bottom. We can look at the evolution of these things across versions of CPUs. For example, from Sandy Bridge to Haswell, there was a doubling of the width of the buses to the cache. There's twice as much bandwidth from the core to its cache to the memory system, basically, in one generation skip that happened. That's a lot. Here's the execution units. They keep evolving from Nehalem to Sandy Bridge and Haswell. We're now past to Broadwell and Skylake. We get more execution units that could do things at the same time. Those execution units can do new things. For example, we used to have vector operations that are 128-bit wide, then more of them, then 256-bit, and now 512 bits, so wider vectors, and richer vectors too. And caches have evolved too. This is what we used to have for caches up until Skylake. Skylake changed that. An important cache people don't talk about a lot is a TLB cache. This is the cache that holds the virtual to physical translations in the CPU. And it went through a huge evolution around the Haswell timeframe. This is just a couple generations ago, where we went from being able to track only tens of 2 megabyte page mappings to 1,000 plus without having to thrash the cache. So what used to be mapped with 4K pages can now be completely mapped with 2 meg pages, which means we get a lot fewer misses in this cache. Layout-wise, servers tend to look like this. They've looked like this for more than 10 years. They probably still look like this for a while. A couple of chips, memory controllers on each chip and directly attached, and some chip-to-chip interconnect. This is the inside of a chip. A bunch of cores sitting on with a shared cache, some sort of a communication mechanism between them, a ring. And this is what it used to look like 4 generations ago, roughly. But then we got to a point where there's so many cores on the chip, they don't really fit on a ring. So we start having things that look like this on one chip, 2 rings with interconnects between them, memory controllers for each. We could sort of think of this as one flat thing, but you can actually configure it to act like 2 separate NUMA nodes and separate it or not, depending on how you want the system to set up. Now this is a fully populated chip. This is the one with all the cores, but a lot of people buy chips with not quite all the cores. So sometimes they're buying that, 1.5 rings. Not all the cores are the same. Not all the distances from all the cores to all the caches even out. There's some interesting mixes. And then we have the evolution to Skylake, which is a new system without rings, more of a mesh. It looks like this. That's what we have in the latest generation. And these are smaller configurations. OK, so that's what we're running on, machines that look like that, not a single CPU with a single cache and a single memory controller. It's important to keep those in mind. Now, I'm going to actually look at some machine code next. And this is only going to be a few minutes. So those of you who really don't like machine code, just take a deep breath. It'll be over, I promise. For those of you who like it, enjoy. The thing I use to zoom into machine code is a tool we call ZVision at Azul. There are other tools you could do the same with. Basically, I put the code I want to look at into a hot loop, fire up our web browser-based profiler, and zoom in and get stuff like this, and then I like to read it. Let's do that for a loop. Here's a really simple loop. It adds all the numbers in an array. And I want to see what the machine code that does that looks like. So here it is. It's very readable, right? Now, the trick that I use to read this machine code is, the reason I put it into a hot loop in a profiler is it lets me figure out what I want to read. See, our profiler tells us where we spend our time. Since I spend all my time here, I know that's the loop. And I don't need to read any of the rest of the instructions. Now I could proudly read this. Okay? Here's the loop. It actually has 2 moves into vector registers, 2 adds of vector registers, and an add around the loop. It probably later takes all this stuff and adds it together, but we can sort of see the read from memory and the add operations on there. So this is on a Westmere, a pretty old CPU, and it uses SSE instructions. 128-bit vectors to do an add. That code is exactly what vectorizers were built to do, right? Just go stream this whole thing and add it, right? Now, the cool thing about JIT compilers is they know what machine they're running on. And hopefully they understand the capabilities of that machine and use the right instructions for that generation. So for example, this is what it looks like on an older machine. Here's what it looks like on a Broadwell machine. It uses different vector instructions. They're twice as wide for each, and there's a load and add operation rather than a separate load and a separate add operation, so it's able to do a lot more per loop. So AVX2 just magically happens because the JIT compiler understands the CPU. This, by the way, is with our Falcon JIT compiler, which we're really proud of at Azul, but generally I'm showing you what you can do when you adapt to a machine. Now, OK, so far I was looking at simple things. This is exactly the demo anybody looking at vectorizing will show you. But let's make it more complicated. Let's take that cool loop and make it harder to deal with. We'll put a condition in there. I want to add one array to another array, but not for every cell, only for the cells that contain even numbers. So I actually test the number, and if it's even, I'll add. If not, I won't. Now, this is exactly what tends to break a vectorizer. If we go and look at the code for that, we'll see that it becomes that. It actually unrolls the logic twice per loop, so each loop is doing this 2 times. Those are the highlighted boxes. And you can directly see the operations. There's a read of something from memory, a test of it, that's the is it even part against 1. Then a jump if you don't like the result, then an add if you don't. It's exactly what the code is doing one by one, right? 1 instruction at a time for each value. And yeah, it unrolled it to do 2 of them in a loop to sort of amortize the loop cost across it. But we're not vectorizing here. Why? Because we have to test whether or not we can do the operation for each one of them. So this is the situation until recently. But CPUs have new features, and those new features let you do cool stuff. For example, the AVX2 instruction set adds the ability to do masked operations on vectors. And this is what the same exact code ends up looking like. Now, this is a little more to read. But let me highlight a stripe through the loop. This loop actually does the same thing 4 times, interleaved for scheduling. But the operations, you see them, are all vector operations. The thing to highlight is not a single if, not a single conditional jump in the loop, other than the loop itself. What it's actually doing is it's reading 8 values into a vector register, each one of those, so 32 of them in the stripes. Then it's ANDing that vector register with something else, probably the thing with all the ones. And then it's testing whether that's equal to some other register, probably the thing with all zeros. And then the result of that is in YMM6. So YMM6 has the true-false value for each of the 8 cells now. It then does a masked move from memory to another register masked with that true-false thing. So only the things for which we had a true result for the if are actually being loaded from memory. It then performs an add of the vector register and stores back only the values that had a true on them. So by using masked vector operations, we can now allow predicates and loops and still vectorize them. That loop used to not be vectorizable. On new hardware, it is. Well, on new hardware, if your JIT compiler understands what the hardware is able to do, which Falcon luckily does. Now that was Broadwell, great. Now the cool thing about, for us, our JIT basically uses LLVM as a backend. So we get to leverage this work lots of other people do. And some of those people are people who work for Intel, so they put in work even before the CPUs come out. And when the Skylake CPUs came out, we said, I wonder what this code will look like on that. And without actually doing any work on our end, we ran it and got this. Now it's using vector registers that are twice as wide even yet, so 512-bit registers. I get 64 operations per loop, because there's 4 stripes of those. There's one fewer instruction here because it uses an even newer predicated vector capability that AVX512 has in it, so even cooler. And the coolest thing for us is we got this for free. We didn't write a single line of code to get this because we use LVM as a backend. It knows what a Skylake can do, and it generates the school code for it as long as you bring the loop to the right form. So that was it for machine code. I promised. Only 5 minutes, right? If you guys like this sort of thing, you could use either our tools or other tools out there to zoom in and see what your actual code looks like. I highly recommend putting your hot code into loops to be able to measure and see what they do. OK, so what is better jitting about? It's pretty simple. It's about raising this level, right? If you can get faster code, your speed will be better in the eventual semi-stable state. That's not a surprise. So let's talk a little about what compilers do to achieve this extra speed, or this speed in general. I'm going to go through very simple step and build up from them. You don't need any basic compiler knowledge for this or anything like that. Hopefully it's not too slow for people. But let's look at what compilers are allowed to do and what they'll do. Here's some code. Not necessarily smart or reasonable code, just code. And the compiler is allowed to take this code and reorder what it does as long as it doesn't change the actual meaning of the results or the observable results. So for example, I could change where in the order this line is executed. It's OK to do that. Compiler is also allowed to remove dead code. So for example, this line actually doesn't do anything anybody can observe. There's no result that you could see outside of this function to running this line or not. Now I could say this is dead code, I can remove it. I could also basically say, let's run this code really, really fast. Nobody will know the difference, right? Remember, every time we remove code, that's like us acting like we did it, but you don't know, because you can't tell. And if you can't tell, we're allowed to do it. So dead code could be eliminated. We don't actually have to run it. We can propagate values directly. We don't actually have to go through all these intermediate temporary things that you wrote in the code. We can figure out where they're going to propagate to and eliminate the middle steps. So we can actually simplify that to that. And compilers obviously know how to do some simple math, like plus y minus y probably cancels each other out, so we can optimize it to this. And those are a really simple step. Pretty much any compiler on any language will be able to do this and simplify the code, right? OK, more simple tricks. We can use the data that we propagate into flow control things like ifs to affect what we do. For example, here's a piece of code that has two possible things to do depending on the value, on the range of the value. Some complicated stuff or simple stuff. But we can see that value equals 5, so we can propagate that through the code and simplify the whole method to this. Right? We know value is 5, we know that bias is 1, we know to return 1. Just eliminate the part of the if that we know won't run. We can cache reads. So a simple way to look at that is here's code that says I want to read from a.x twice. I'm allowed to read once and use it twice. I can put it in some temporary value, temporary register. I don't have to read it again from that memory location just because you wrote it, right? And I can do that as much as I want. So not just 2 into 1, I could do a lot into 1. For example, here's a piece of code that says loop as long as nobody has set this flag. And the compiler is allowed to optimize it to read the flag, put it in a register, and loop as long as the value of my register isn't changing, which it won't. This is an infinite loop. This is what the word volatile is for. It's to say, please don't cache this read. You have to read it again every time I say, because I'm actually interested in what other people might have done to it. If you don't say volatile, you don't mean read it again. Okay? You can similarly eliminate redundant writes. So for example, if I wrote to the same location multiple times, I could say, if I wrote really, really fast, you will never see those other writes, right? So since it's possible that I ran so fast you'll never see it, I don't actually have to do the things that you might never see, and I'll just do this. So redundant writes can be eliminated. Again, doing this in force, rather than running a loop with 1,000,000 stores, we can just do the final store. I just eliminated 1,000,000 iterations on a loop because I can redundantly eliminate the writes. Inlining. Most people know what inlining is. It's taking a function and pulling the code into the caller. Here's a method that is final. We know it's the only method that does this thing, and we have some place that does thing get x. I can optimize this code to just read the field directly, don't make a method call. Now, this is the simple meaning of inlining, but this is not where the real power of inlining comes from. Yes, I eliminated some overhead of making a call, but the real power of inlining comes from propagating optimizations into that code. For example, here's a variant of the previous code, but now I don't know what value is. Right? It's a parameter, so I don't know which way the if is going to go. But I have a caller that's calling this with a 5. If I can inline that code, I can propagate the 5, and I could optimize the entire method away. This goes to a very deep scope. This is why JVMs will inline 9 deep sometimes, just to get more of the optimizations, the other optimizations in, and applying to more of the code, because you can now optimize across these boundaries. That's the real power of inlining. Now, those were the simple things that most compilers do. I'm going to go and measure some stuff, a little like that hot code loop thing that I talked about, but let's try to measure how fast things go, and I'll show you some simple problems. So for example, I want to see how quickly I could do plus plus. So I'll put a loop around some plus plus and measure how long it takes to do this loop with some sort of framework. And if I measure it, I'll find out that I can do this loop really, really fast, like this fast. And that's so fast, it's probably not reasonable that this is really a good measurement, right? We don't have any hardware that can do this fast. It's just an impossible result. So something's going on here. Probably the compiler is figuring out some trick. It's too simple to measure, so let's make it a little more complicated so we can actually measure it. Maybe if we do the math, something that accumulates different values like plus equals I, and then it's more complicated, maybe I can make the compiler not optimize that away, but that also is impossibly fast. The reason for it in this code is the entire method is dead code. This is a void method with no memory side effects. Whatever happens in it, you're never going to see, so I can just return. We're just measuring how fast we make a method call. That's all we're doing when we're measuring this thing. So what can we do to defeat that? Because we're actually trying to measure how fast this thing is. Well, we can propagate state out so that the compiler can't optimize it away. So I'll return the sum. Now I've got something somebody else can observe, so I actually have to compute the result, right? So here's the loop. We'll measure that. Turns out, unfortunately, that's still impossibly fast because the compiler knows that the final value of sum is going to be count. So it eliminates the loop. OK, so let's try and make it more complicated. Let's go back to the idea of, OK, something more complicated, and we know the value is going to be this at the end. Now we actually have to do math. Is this better? Well, it is better. So both regular hotspot, OpenJDK, and our previous version of a JIT compiler on Zing looked at that and actually ran it. Unfortunately, with Falcon, the compiler is smart enough to say, that's an arithmetic series. I know how to do count times count minus 1 over 2, and I don't have to run a loop. Again, one of those things we didn't build. LVM, lots of people work on it. Some academic person somewhere, I don't know who you are, but thank you, probably sat there and thought it would be cute to recognize an arithmetic series and optimize it away. I don't know what that's good for in the real world, but it's great for defeating benchmark measurements. OK, so it used to be good enough to make the compilers not figure it out. Now it isn't. And that's the lesson here. Things change, OK? So how about this? It turns out you can prove the result is 0. Here's what I do today, highlight on today, to beat all the compilers I know of in Java today. Like, if I do this on everything I know of, it doesn't know how to optimize it and actually measures it, OK? Now, notice that since I put a slide up here, some guy is going to say, there are only 8 possible ways for that to look. I can optimize that. But for now, they haven't figured it out, right? OK, so those were some micro-benchmarks. What are the takeaways here? First of all, it's hard to micro-benchmark and figure out if you're actually measuring speed. This is tricky. So you need to sanity check everything you do. Just sanity check and figure it out. And not only sanity check the code the way you wrote it, put in sanity checking code, because things that work today might stop measuring in the next JVM version you get to run on. So even though it currently measured, maybe it'll stop measuring tomorrow. So sanity check everything, disbelieve everything. If you give the thing this twice as much work and it doesn't take any more time, something is wrong. Right? If I increase the loop count and it doesn't get longer, probably wrong. That's an easy sanity check. Anybody here know what JMH is? Good. So more of you should too as well. So use JMH, use JMH, use JMH. It's basically a framework for running micro-benchmarks. It's with OpenJDK. It helps save you from a lot of mistakes in building micro-benchmarks. However, even with use JMH, you should sanity check everything. Why? Every single micro-benchmark I just showed you was run with JMH. So JMH doesn't magically make these problems not happen. It makes other problems not happen. OK, so that was our micro-benchmarking detour. Let's get back to compiler stuff. We talked about simple compiler things. JVMs get to do other compiler things that are hard to do in static compilations. They get to speculate. They get to hope that something is true, even though we can't prove it's true, because we can detect if it becomes untrue and throw away the code. We can't do that in a static compiler, because we can't come back to the compiler and ask, give me other code. And that gives us a lot of power to optimize things even further based on that. A lot of the speed in current JVMs comes from the speculative optimization capability, probably more than half. Here's an example of speculation. I have this code. I don't know which way it's going to go, but I've run it 100,000 times, and it's never seen a value bigger than 10. So I can speculate that I'm not going to see a value bigger than 10. A common term used by speculative compilers is uncommon trap. It's, if this happens, just, I don't know, give up. Go to the interpreter. Don't run this code. It's not correct. It's the get out of here, right? But if that doesn't happen, I know what the result is. Now you could look at this and say you could have put the slower code under that if, and yes you could, but this becomes combinatorically complex and hard and creates really big code if you're inlining 9 deep and doing every possible if in all combinations that way. So it becomes untenable very quickly. So the ability to say, I just don't want to deal with that case, just get out of here, is very powerful. A really simple speculative optimization a JVM can do, and you can't do in a static compiler, is a null check elimination. So every time you write Java code that accesses a field or an element in an array, what you're actually writing is equivalent to that statement. Not just access the field, but first check that I'm not going through a null. If that is a null, throw a null pointer exception, but otherwise, let's do the thing you said. Every single field access you do does this, and if we actually executed that, it'll be slow. We don't want to do that every time. What the JVM will actually do is say, I don't think you're going to give me a null. I'm just going to access through this thing. What's the worst that'll happen? Well, you gave me a null. I'm going to take a segv. The JVM will intercept the fault. It'll say, wait, before I crash, where did this happen? Oh, it happened there, and I limited a null check there. I probably should throw an exception and not actually crash. And that's exactly what it does. And by doing that, it eliminates all the null checks on all the field accesses you do that are not actually seeing nulls, which is hopefully most of them, right? Now, if you do see a null, that is expensive, as in 100,000 times more expensive than the if would have been. So it better not happen a lot, right? You don't throw a lot of nulls, I hope. But what the JVM will do then is say, OK, I've got this really weird, bad code, and it's throwing null check exceptions all over the place. If it does it too much, right now too much is more than twice for that point in code, it'll just de-optimize the code, put the if in it, and run it with the if, because it doesn't like taking segvs all the time. But it'll assume that you won't throw segvs. If you do throw them, then the code will evolve to handle them fast. Right? But then we get to throw away all the other checks that are not necessary, because we've got virtual memory hardware that does it for us. Class hierarchy analysis is a really cool set of optimizations. Basically, it relies on the knowledge of the JVM of the entire code as it stands right now. So we can see all the code. We can analyze things about it. We can assume things based on that analysis. And then if we later load a class that breaks that assumption, we can say that other code needs to disappear before this class gets loaded. So that linkage of I can register assumptions, I can check whether the assumptions are still true before I load the code, I can blow away code that makes wrong assumptions, but I don't have to blow it away if the assumptions are still true, is very powerful. Here's an actual example of how powerful it is, and this is actually responsible for the fact that most people write clean object-oriented code in Java. If this optimization wasn't true, we would be writing different. Remember this example I gave you before of trying to inline a method? Well, if the method is final, we know we can inline it. But what if it's not final? I mean, if I make a method final, I've stopped the extensibility of, I can't extend this method anymore, right? I can't override its behavior. I have an animal here. It's got some color. Most animals are going to return that color, but maybe somebody someday will need to override it. I want to extend the code later. So what can I do about this? Well, with class hierarchy analysis, we can actually sit there and say, OK, the code has a virtual method call in it. But right now in the known universe, I have cats and dogs and birds. And none of them have overwritten getColor. There's only one implementer of getColor in the known universe. That's it. So I can actually inline the code. That is why getters and setters are free. This is why we don't have to expose fields to the outside world. This is why we don't have to put finals in our getters and setters. This is why we get clean, encapsulated, object-oriented code. It's all because of class hierarchy analysis. This is true as long as only one implementer does this, which is the case for most getters and setters, right? So class hierarchy analysis is very powerful. But what if we did override getColor? What if we had this thing and now we put a chameleon in the universe, and a chameleon derives its color from the branch that it sits on, so we need to override it. And now it broke the assumption, I threw away that nice optimized code, I still want to run this, and I still want to run it fast without a virtual call. Well, I can't prove that that will work, but if I look at this code and for some reason this code is part of a dog kennel, and dog kennels have only seen dogs, they don't see chameleons. The optimizer could say, based on that profile, I'm going to guess that this is a dog, and if it's not a dog, uncommon trap, I don't know what to do about this, run slow. If it is a dog, we know what to do. That's a guarded inlining, or a guarded static call, if you'd like, with an inlining after it. That you can do, again, a speculation based on a profile. Now, I give you examples of speculation. I think, yeah, we're good on time. Good. Speculation relies on the ability to be wrong, on the fact that if we find out that the speculation is incorrect, we can blow away the code, and that's what de-optimization means. We've optimized speculatively. De-optimization means throw away that code. Without de-optimization, we're not allowed to do these speculations. So de-optimization is a key feature we need to make all this code run fast. And going back to this picture, de-optimization is what these backward spikes are about. We evolved the code, it went into the blue stuff, it made some guesses, some of them were wrong. When it hit the wrong guesses, it de-optimized, went back to the interpreter, went through the cycle again, remembered the wrong thing, so it's not going to do that again, and optimized, knowing that, hey, you are throwing null pointer exceptions in that place, or there are sometimes are chameleons in dog kennels, or whatever it is it ran into, right? That's why we get these spikes. Now, these spikes happen not just at the beginning. They happen when reality changes, when the behavior of a program evolves to new things that just haven't been experienced before. And that makes it a little bit difficult to know if you're done optimizing. So you're probably done optimizing if you see no more optimizations, but you don't know that you're done optimizing because you've run 100,000 things through it, or because you've warmed it up and it stopped compiling for now. For example, well, I'll give you an example in a second. So micro-benchmarking is hard, but warming up is even harder, because you really, really don't know when the de-optimizations are done happening. And there are many, many potential causes for de-optimization, including the initialization of classes or non-initialization of classes and any value that we might speculate on. But let me give you a practical example from financial services. Suppose you're trading, and suppose you care about running trades fast. People care for some reason about that. And you want to be fast when the market opens. Right? You don't want to run interpreted code for 10,000 operations and then go fast. Other people will make a lot of money on you if you do that. So you're going to train your system. You're going to warm it up before you actually run the first real trade because you want to be fast. How do you warm it up? Well, you give it fake things to do. You get yesterday's trades and you run them through, or you make stuff up, whatever it is. You give it 20,000, 100,000, whatever enough is, get the JIT compiler to run, warm it up, see that all the compiles are done. Now I'm past that initial warm-up phase. Now I'm ready for the trade. Well, that sounds really good, except that if you're doing fake stuff, it probably goes through different code paths somewhere, if you're not careful, super, super careful. And for example, if it's a fake message, maybe we don't really want to send it to the exchange, or maybe we'll send it in a different way, or maybe we'll tag it in some other way. Anything you do different in code about the fact that it's fake is different. And guess what? You just did 100,000 fake things. What do you think the JIT compiler is assuming you're going to be doing? Fake things. Its basic optimization is, look, they're never trading. Let's optimize for not trading. So what happens in the first trade? You de-optimize. You're running interpreted code for a little while until you learn better. That's what's hard about this stuff. The actual warm-up ends up looking like this. You got this nice warm-up, then you get hit with the actual reality. And you get to be slow for a little while. Or the evolution is all the lazy loading and aggressive optimizations and evolution we showed before, and then boom, the optimization is this part. So what can we do about this? Well, this is where, at Azul we actually make JVMs that address some real-world problems. Not all of them, but some of them, like this one. And what you can do about this, for example, is to log and replay optimizations across runs. So imagine that you can actually say, while I'm running today's stuff, let's just record all the stuff we learned. All the optimizations that happen, all the inputs to them, all the profiles. Eventually, this thing will stabilize, at least enough to see the entire experience of the day or the week or whatever we did. And then next time we run, we'll just say, could you please start with that? And we start with that and we just prime all the profiles to that. Whatever we learned, what the profiles are, what to do, what not to do, so we don't de-optimize if we do it. And then you just load the JVM and make it run through that stuff before you trade, or before you put it in the market, or before you put it on your load balancer for a web service. You can even build a workflow that'll say, can you please tell me if any of the optimizations that have been applied yesterday have not yet been applied on this run? And if so, why? For example, maybe there's these 5 optimizations that were done yesterday but not done yet. And maybe the reason for that is you haven't initialized those 15 classes that they depend on yet. So if you initialize them, then we'll get the optimization. You can work this so that the list will be 0. So you know that whatever got optimized yesterday is already optimized before you turn on the first transaction. That's a cool thing. And that will basically load this thing up and also flatten the warm-up itself, because you don't have to learn from doing 10,000 things. You already have the learning from the previous run. What does that do to the picture? Well, it pulls it up to the left, right? All that warm-up experience could become not entirely vertical, but a lot more vertical than it is today. So we've improved the speed by optimizing more, and we've improved how early and how quickly we get to that speed. What else is missing in this picture? Well, we have these dips. Right? Even though we're going fast, and even though we go fast from early on, we still slow down to an absolute 0 every once in a while. And that's where actually solving the GC problem comes in, to make speed actually work consistently. So this is where I'm going to brag a little bit. We've got a few minutes for me to brag, I think. Yeah, tiny few minutes. The C4 collector is a collector we have in Zing. It basically eliminates GC problems. It makes an application that behaves like this, behave like that. I don't care what the application is. If it behaves like that and garbage collection is involved, it'll behave like the thing on the right. This is Cassandra, by the way, but a low latency app is just the same. It also makes tuning a lot less needed. So for example, some of you might recognize some of these flags. Okay, yeah, some of you. For example, maybe on Monday you need this and on Tuesday you need that. Or maybe somebody changed the code, or maybe just different applications, who knows. Here's some more flags you can study about. Or you could just say, I'm sick of putting duct tape on my application. What if we just use a modern collector that doesn't need tuning? And let's just give it a lot of heap. But then that's a waste, right? So squeeze it, and squeeze it, and squeeze it, and squeeze it. Do that until it breaks. Then turn it back 2 notches, go home, you're done tuning. That's the real world experience that you can have today. By the way, this is Cassandra running on a AWS cluster with no tuning. That's the 1 millisecond pause point. This is not a low latency system. And things could become really, really good if you do that. For example, if you actually have workloads that have SLAs, like these, for example. These are not very aggressive. And you want to know how many machines you need to carry that workload without making your customers angry. Then you can measure that. And this specific case from Improved Digital on AWS is, they got this many transactions out of a well-tuned hotspot with 2 months of consulting. And they put it on Zing, and they got that out of the same AWS machines. This is not because we get the compilers to run faster or the code to run faster. That's only 13% of this. We are faster running this, but not that faster. This is because you could just push the machine harder before it cracks, because those dips are what makes the SLA break. And you could basically take behaviors that look like this with success rates that fall with load to behavior that looks like what happens on the right there when you convert to sync. So what this really means is we have the features that do all these three things. We have Falcon that makes the speed bigger. We have Ready Now that brings it up and to the left, and we have the garbage collection that flattens it out. And basically, you get to start fast, go fast, and stay fast, or come closer to that flat ideal that we want to have. So that's the small commercial at the end. At this point, I'll take Q&A if there's any time left. I'm not sure if there is. How are we on time?
We've probably got time for one question, I reckon.
OK, good. Thanks.
Hi, so you said that you can optimize by replaying the scenarios. How would this work on an updated code base? So you're running the same application, but with some updates.
It's a very good question. So the way we actually perform this logging of optimizations is on a per method basis. We actually log the optimization input to the compiler when it actually got triggered. We check some of the methods, we verify they're the same. If you change the piece of code, whatever we logged for that piece of code, for that method, won't apply anymore, and it's done actually on the class basis. So all the methods in the class are going to blow away. So for example, if you're doing continuous deployment and you're updating 20 times a day, hopefully you didn't rewrite the whole code 20 times a day. So the profile won't apply to that code, and that code will go through the normal learning process. None of the learning process is gone. It's just a priming exercise. But the vast majority of our code will start really fast, which hopefully is thousands of different things that we saved you from going through.
What's the worst workload for Zing?
What's the worst workload for Zing? I write a lot of really, really bad code for Zing. I mean, I write torture tests for Zing and for other JVMs. You probably mean something like, what's the worst real-world stuff? I would say the main thing that we don't try to do is fit into tiny pieces of memory. So we round the heap up to a gigabyte. So things that try to work on 200 meg and stay there may as well not use Zing. But above that, if you're running more than a gigabyte of heap, you should expect good behavior. Now, is it better behavior that you care about? I don't know. What matters to you, but there aren't things where we kind of, we suck at that, right? There isn't some big, you pay big time for performance somewhere. It's just a bunch of good stuff. We are a server-focused JVM, so we're not trying to run in clients. We're not trying to run on desktops well. We're not trying to run tiny workloads. We do run microservices very well because most of them don't necessarily mean tiny size, but tiny functionality. So, yeah.
Does our programming style impact the performance? For example, if I prefer write more functional code like lambdas and collectors and streams instead of pure cycles?
So does programming style affect performance? To a degree it does, but the thing I would warn you against is to actually start writing in weird ways to beat the compilers. If you go back in history, you'll find all kinds of cool recommendations like make all your methods finals to make them fast. And if you Google for performance tips for Java right now, you'll probably find this because Google doesn't forget, which is sad, right? So at a point in time, you might find something that currently makes it faster, but if it's not idiomatic, you're probably going the wrong way. So writing clean code using good code practices, yes, do that. Shifting to code practices that are also idiomatic for speed, that probably makes sense too, but starting to do things weirdly just to get the speed, only if you really care about that and you're willing to do it every 2 years again. Because what you do now might slow it down in the future. You asked about functional. Functional coding practices are generally idiomatic in Java now with Java 8 and Lambda functions. We have languages like Clojure that, and Scala, but Clojure strongly encourages, as Car makes it, if you want it, right? And they don't hurt in themselves. They might generate a little more allocation load on a system because you tend to create more immutable, short-lived objects when you do that. But actually compilers and, both compilers and escape analysis and collectors with generational collection are very well optimized to deal with those. So I'd encourage you to write good code first and then optimize it rather than write it from the start to the speed. Any other?
If I want to dig deeper into this topic, are there any books that you can recommend?
Deeper into the topic in books. Well, obviously, if you want to, on compiler optimizations, there's lots of material out there. It's not specific to Java, but a lot of stuff that's not specific to Java is applicable here. Outside of the compiler stuff, I don't think there are a lot of books, but there's academic papers on these subjects. So generally looking for performance optimizations in Java on Google Scholar or something is probably a good idea. Yeah, I think there was one last one here, and we're probably out of time at that point.
So last I read the spec, Zulu is demanding a minimum spec of, I think, 32 gigs of memory and 6 cores. How well does this play in modern environments where people are looking at much, much lighter weight deployments based around containers?
So first correction there is that's Zing, not Zulu. Zulu is our OpenJDK variant. It's exactly OpenJDK, runs everywhere OpenJDK does. With Zing, unfortunately, somebody has really stale material, if that's what you read, or maybe it's very dated. Zing will run well on 1 core and 1 gigabyte, if that's what you need. That doesn't necessarily make it a great idea, but when we first did that, it was because we were trying to avoid all the, I'm trying to run this in this tiny box, please help me things. That was a few years ago. Now you can have Zing for a free trial, and it tends to work pretty well, runs well in containers and others. I would say that, given that we have a concurrent collector, for example, you usually want more than 1 core just to let the collector run without you stopping, because otherwise you're going to look at these 10 millisecond context switches things, right? But that's probably still much better than a half-second pause, right? So it's all a relative statement, right? We add value to 1 core. It's just you don't want to run low latency trading on that. Yeah. And I would say, as I said before, there are sizes below 1 or 2 gig. It just doesn't matter. But above that, we've gotten to a point where we think we're pretty roundly applicable.
Thanks very much.
Thank you, everyone.